Video lecture videos on compilers. Compiler is fun. I am Subhiran Chattopadhyay, Vice Chancellor of Techno India University and former professor of Jadavpur University. I prepared this lecture video for anyone who wants to know about intermediate code generation. We have already talked about the background of intermediate code generation and the intermediate code generation approaches for arithmetic expressions in our previous lecture videos. Today, I'll be concentrating on a very simple Boolean expression and also simple arithmetic and conditional statements. The approach that I will be taking to generate the code is not necessarily unique. In fact, it is not unique. There are many different approaches. I'll be taking the approach in which conditional and unconditional statements are used, and a very interesting but nice concept of backpatching is also used in that particular domain. There are many other approaches, but the same kind of technique is used everywhere. So even if you are studying or reading a different kind of an approach which is also available in books, that understanding that we'll be getting in this lecture video will be crucial to understanding anything that will be written and that we'll read in the books or the materials. So let us start with a very simple conditional expression x less than 5. X less than 5, for x less than 5, the three address code generated is a combination of two jump statements, two go to statements. First one is conditional, if x less than 5, go to somewhere. And the second statement is unconditional, which is go to somewhere else. We can very easily understand that where do I go to is not known now. Why? Because the context in which this particular condition is used is not known to us. So the go to for statement number 1 have to be filled up. The target of this go to has to be filled up by the line number or the quadruple number where the code for execution, once this condition is true, is written. That part of the code is not known so far, and therefore we cannot fill up the target of this group. And we have to remember that this particular statement number 1 or line number 1 or quadruple number 1 contains a go to whose target is not filled up. So since I have to remember that, I remember that in a list called true list. The connotation of true list is in case this condition is true, then you reach these kind of line numbers like line number 1, and that contains the go to which is not complete. Once the target of the go to of this line number 1 is known, we have to fill up that particular statement. Similarly, in case x less than 5 is not true, then you will come to line number 2, statement number 2, quadruple number 2, and that particular start line number of the part of the code has to be written down as the target of this group. So let us see in detail the context in which this condition will be used and the kind of actions that I need to take in case I need to generate a complete code for that. Let us see the context first. So see that this is the context. This is the context, right? This is the context. Also, for the sake of simplicity, these brackets will not be there because our grammar will not have that. So if x less than 5, then assign 5 to A, else assign 6 to A. This is the standard sentence that I will be using. I need grammars. I need a grammar for generating statements. So there must be a non-terminal which will generate the statements. We are just generating two types of simple statements. One is arithmetic expression. One is assignment statement, that is id assigned E. We all know that E stands for an arithmetic expression. So E will contain the underneath this E there will be a parse tree which will generate an expression, and the value of that expression or the placeholder of that expression will be assigned to ID. But the simple conditional statements, I have if C condition, then a statement, else a statement. Whether this grammar is ambiguous or not, that is not my question as of now. We can work with ambiguous statements to understand the basics of tree underscore generation. So there must be a grammar for E. We know the grammar for E in our last lecture video. In another lecture video, we know this grammar for E. Out of these many rules in that grammar for E, only this particular rule will be used. Similarly, the minimum grammar for condition generation could be just C produces ID or E. Of course, you can argue that I can have ID less than, greater than E, and so on and so forth. Yes, we can. For the time being, just for an example, I am using only one rule, and we can always extend that to other rules if it is needed. So, if these are my grammar rules, this and these are my grammar rules, and this is my sentence, then what is the parse tree? What does the parse tree look like? So the parse tree, as you can see, if x less than 5, then in the entire thing, then else this entire thing, right? I mean, in fact, this goes here and comes back, and then I do the complete reduction. If I look at the number of reductions, this reduction is number 1. This reduction is number 2. This is number 3. This is 4. This part is 5, and this entire part is 6. So let us have a look at each one of them one by one. As I said, the first reduction will be here. Now, I told you that this part of the tree will be erased. You will not remember this part. So you have to generate these two lines, right? So to generate these two lines, you have to write these two statements. Not a problem. Emit. But you need to remember what is the line number where target should be filled up in case the condition is true. So that is my true list. And what is the line number where the target is filled up if the condition is false? That is my false list. So remember that in C.tl and C.fl. True list, T list, TL, false list, F list, FL will be used kind of interchangeably, because sometimes for the sake of space we'll reduce the space by writing TL. If I have enough space, I may write true list like that. Now we assume a function next word that returns the serial number, not the number, the serial number. The serial number of the next quadruple. Like, and as of now, I did not generate any single quadruple, any single line. So what is my current quadruple? 0. What is my next quadruple? 1. So this returns me 1. This returns me 2. So C dot true list is 1 and C dot false list is 2. And that's how I go to at this stage. I generated these two lines. I remembered C.tl is 1 and C.fl is 2, and then I go to the next reduction, which is this reduction. Once this reduction is done, all of us know what happens. What happens? E.val is 5 and this part of the tree is obliterated. What is the next reduction? Next reduction is naturally this one. This is a new rule. We do not know the action that is to be taken here, but I know what is to be done. I know that one more line has to be generated. So I generate a assigned ID assigned the value which is stored in E. So this line will be generated by this particular code, and I go to the next reduction, which is this. Once this is done, E.val is set to 6, and the next reduction is this one. Again, a similar rule, a similar action, another line that is A is assigned 6. Very nice. And then once this is done, this will entire story. Very nice. Only problem is what should we put as in put in the target here? What should we put here? What should we put here? Intuitively, I know that 3 has to be put here. Intuitively, I know 4 has to be put here. But where is the written down? Where is the remembered? It is not remembered anywhere. So that is the question. What should we put in as the target of C dot TL 3, as the target in C dot FL 4? But that is what we know because we are human beings. We are intelligent. How do I know that? We have to change the grammar a bit. We have to put a marker non-terminal and remember the next quadruple number in it. We'll go to the detail. Before I go to the detail, we check that this code is not the proper translation of this line. I have a bad habit of making my viewers or making my students work a little. I want to know in my reply comments what is wrong. If I say that this has been translated to this, what is wrong in this translation? Tell me in replies what is wrong in this translation. This translation is not really correct. Don't tell me that this is because of these two dots. No, not that. There is a gross mistake in this particular code. But that does not matter much as of, in our current discussion, we can go ahead. And when the time will come, I'll tell you what is wrong in it. But not at this instance, at this instant. So let us change the grammar a bit. Again, this is my sentence without the parenthesis. The same S, this part remains as it is. But you see this M here and this N here, two more non-terminals. What is M doing? Doing nothing. What is N doing? Doing nothing. Then what is this? They will not add anything to the sentence, but they will remember the next word. What is meant by next word? Recall. Let's say you have generated 3 lines, 3 quadruples. So what is your next word? 4. If you have generated 10 lines, then what is your next word? 11. Like that. So we'll be adding an attribute Q to M and N, and will add an action M dot Q equal to next word. So M dot Q, you will remember where should my sentence code for next line. Where should I go in case my condition is true? M dot Q will remember, but immediately it can write that out. It can write that out only when the proper reduction takes place. So let us redraw the first 3 for the same thing. You see, this almost the same thing. If this one, then of course you go there, then this one, then you go to else and N, and then come back, and then you are this way, you are this, right? That's what it is. So let us look at the reduction steps one by one. This reduction step is known to us. The actions are already explained, nothing more to explain. So we generate this code and we remember this thing. Now see, without any input, this this reduction has to take place. So naturally this reduction has to take place on epsilon. So nothing can be generated out of it, but it has to remember something. What does it remember? It remembers the next word. So how many lines are generated so far? 2. So what is the next quadruple number? 3. So m dot q will remember that I am 3. After m dot q is 3, this action is taken. What is this is the next reduction. And as you all know, in this reduction, e dot val is set to this particular value, which is 5. Once that is done, this particular reduction will take place. Once this reduction takes place, we talked about the semantic action, we talked about the generated code, and we go to the next reduction, which is this one. How many lines we have generated? 3. How many quadruples we have generated? 3. What is the next quadruple number? 4. So n remembers 4. And after that, I go to this reduction. Once I go to the reduction, e dot value is set to 6, and then the reduction for the arithmetic for the assignment statement. In assignment statement, what happens? This particular line will be generated, and then I go to here. Now you see that m dot q remembers where the code should go in case the condition is true. Where the in fact I can stay here. Yeah, sure. Where should I go in case my condition is true? So what are the line numbers where there are incomplete go-tos for such question? What is the question? The question is where should the control go in case the condition x less than 5 is true, right? So that's the line number 1. In line number 1, that this says that in line number 1, I have in an incomplete go-to whose target is to be filled up by the place where I should jump, the control should jump once the condition is true. So where is that? That is here, m dot. So fill up your c dot tl by m dot q and fill up your c dot fl by n dot. Now I will tell you where something went wrong. You see, here I must have a go to. Why? Otherwise, if x less than 5, I do this. Sorry, I do this. Not this. Then I come here. I also come here. So unconditionally almost I have to come to the line number 4. If x is less than 5, I also come to the line number 4. If x is greater than 5, also I come to line number 4. So in this n, in the semantic action for this n, what I should have written? I should have generated this good. So in m, just m dot q equal to 3 would be a correct semantic action. But in n, the correct semantic action would be first write down a go to statement, then remember the next quadruple, and that in that case n dot q will be 5. And then this part of the tree will be executed. So line number for this will be 5. And once you come back, your c dot fl will be filled up with 5. And this go to will not be filled up. Why? So when will it be filled up? When I know after this statement, the statement that was if x greater than 5 go to a equal to 5, else a equal to 6. Assume that after that I have b equal to 7. So this go to should go to b equal to 7 at line number 6. At line number 6. So who should remember that? Who should remember that in line number 4 there is an incomplete go to? S should remember that. And this will be detailed when you talk about compound statements. We just talked about, frankly speaking, simple statements. We need to talk about conditional statements as well. And when we talk about conditional statements, we'll see that this S needs to have one attribute, which is that is S dot next, meaning the whole block of S, which contains these 4 or 5 lines, that will contain certain go-tos, which cannot be completed, which cannot be filled up with the targets before the next statement. The code for the next statement is generated. So we'll come back to that again. So it will be a very nice thing to understand the compound statements. But to go there, before you can go there, we need to, complete three-address code generation for more complex conditional expressions like condition or condition, condition and condition, or a combination of all this, and control for statements like while loops, like like uh, like while loops, like maybe until, maybe like for loops, maybe at least while loops, right? So with that, I come to an end of today's lecture video. You should, well, the way to learn anything is to learn the problem, get sufficient 2, 3, 4 instances of the problem, like examples of the problem, find out a solution to those examples, and thereby try to find out what could be a general method to solve it. In this instance case, for three-address code generation, find out the grammar first, then take a few sentences, create the parse tree. These are the steps. Find out the grammar, create some examples, create the parse trees for every example, find out the reduction steps, and for each reduction find out what we need to generate as code and what we need to remember, because we could not generate everything and I need to come back to this code again. Understand that once you reduce, the part of the parse tree is erased, is obliterated. You cannot have an access to that part of the parse tree again. If something has to be remembered, you need to preserve it in the root of the subroot of that particular tree, which is erased. The parsing algorithm will call your semantic actions during reduction. Unless and until you change the parsing algorithm, which is not in your hand, you will not be able to manipulate there. So you have to go with the flow of the parsing algorithm. Everything that you have to remember, you can remember as attributes of the non-terminals, as global data structures. But nonetheless, you have to remember things. You cannot expect that later on, the part of the parse tree that is reduced, that is proved, will come back again. You will not be able to see that again. The major use of compiler learning is in language translation. Lots of language translation activities take place, and that is the major use of. I mean, you don't devise a new parsing algorithm. You will only write an LLR person, use a standard tool, generate the parsing table. But you have to write what you want to do with the parse tree. What is the code that you need to generate? What is that? I mean, you may need to translate from one language to another, right? So, I mean, one programming language or high-level language to another, not natural language. Natural language translation is difficult. So, understand the basics of things which you will remember years after your studies. The basic concepts, not the details. With that, I come to an end to today's lecture video. Maybe today or tomorrow I'll give you one more lecture video for the next level of translation of surface loops. Thank you very much.